Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about functions of three or more variables. And we're going to apply partial derivatives in doing that. Okay, so let's do a brief recap of what we did so far. So basically, we talked about partial derivatives and its geometric interpretation. And in a previous video, we talked about how to solve such a function if z was defined implicitly, so it's not an explicit function of z. And here in this case, we use, from what we learned in Calculus 1, we used implicit differentiation because it's implicit, right? Um, and now we're going to explore how to take partial derivatives, particularly with functions of three or more variables. Okay, so partial derivatives can also be defined for functions of three or more variables. For example, if f is a function of three variables x, y, and z, then its partial derivative with respect to x is defined as this. So if you want to find the partial derivative with respect to x, here we're given a function of three or more variables, and this is its derivative. So we take the limit as h approaches 0, we have x being the one that changes, we have y, we have z, we subtract our original function, and we divide it by h. This is the limit definition of a derivative, which I did discuss in a previous video. Okay, and what this limit is basically telling us, well, it's found by regarding y and z as constants and differentiating that function of x, y, z with respect to x, right? um, so here, let me just say, what's this? This is found by treating y and z as constants, right? And we differentiate it with respect to x. We don't need to say that. Yeah, because if I know that if we're treating y and z as constants, then most likely we're doing it in respect to the other variable that's not a constant. So here we say if, let's say w is my output, because we already used x, y, and z. So we'll use w. Um, then we can say that it's f sub x is just the partial of w with respect to its x, right? And we can interpret this as the rate of change of w with respect to x when y and z are fixed. Unfortunately, or at least what this textbook says, is we cannot interpret this geometrically because then the graph of f would lie in a four-dimensional space. And so in general, so unfortunately, we cannot interpret this thing. Unlike in our previous one where we were able to do that in 3 dimensions or 3D, but in 4D and beyond, I don't think we can. Or at least not with the tools we have or we learned so far. Okay, so just to make it general. So in general, let's say u is a function. So here we're just going backwards. Okay, so we have u. It's, let's say, a function of n variables. So not even two, not even three. We're just making it general all the way to n. And so we're saying that u is some function that has some values x1, x2, all the way to xn. Then we're going to say its partial derivative. So what is it? With respect to some variable here, let's say the ith variable, xi, is this. So I'm taking my partial with respect to x sub I, and this is equal to, again, my limit definition. And so this goes from f, my function, right? F of x1. Here we're assuming it's not x1. But again, I'm not sure. And let's say we have some middle interval here. Xi minus 1, and then that current value xi plus h, right? Because this is the one we're doing that. And then we have xi plus 1 all the way to xn, right? So that thing. And then we're going to subtract that to f x1, xi, all the way to xn. And then here we say, okay, it's a kind of a general long limit. All of that is divided by h. Okay. There's also other notations to write it. So we can also write it like this. The partial of an f with respect to that variable xi. Could even write it as f of x sub I, f sub x sub I. We could write it as f sub I or di or d sub I f. Right? Okay, let's do one example of these. So here we're being asked to do an example. What example is this in the textbook? 6. We're being asked to find some things here. So f sub x, f sub y, and f sub z. That's the new one. And here's our given function of 3 variables. This is equal to e to the x, y, ln z. All right? So first let's do f sub x. How do we do that? When we do, actually we don't even need this. When we do f sub x, right? Well, we make y and z numbers, right? We make them numbers. And so we just take the derivative of that. What happens if this was a number and this was a number? Well, okay, let's take the derivative of this whole thing. Here I can see a product rule. This is definitely a product rule. There we go. And from there, what do we see? We take the derivative of this thing. Well, this is just what? It's e to the xy times chain rule, so this one, times this thing, plus e to the xy, chain rule of this, well, this is just a number. So actually, this is a 0. So if that was a 0, then completely cancel, right? Gone. This one's gone. Because the derivative of this is a 0. So we're left with this. Now what happens? We have xy. Well, here we treat y as a number. And x is just, well, if we take the derivative of x, that's 1. So we have y. So we're actually just left with y, e to the xy, ln z. And we're done, right? And now let's do f sub y. And so again, we just, actually, I'm mostly just going to copy this whole thing. Because the setting up is mostly the same. The only difference is how do I treat each one of them, each of the letters, right? Is it a variable? Is it a number? Here I do f sub y, so I treat my x and z as constants. So how does that work? Well, okay, I take the derivative of this thing here. Here my x is a constant. So I actually get e to the xy. And then I do a chain rule here. Then here I just leave this be. And then what happens to here? Well, we copy. And then in this one, ln z, z is a constant. So actually this turns into a 0 again. And so I'm left with this again. And then what happens? Well, now my y, or no, my x is a number, right? My y, when I take the derivative of this, assuming x is a number, well, I'm just left with x. So here the difference is just I change my y to an x. That's the only difference, right? Lastly, for my f sub z, well, here I kind of do the same thing. Okay, what happened here? Okay, yeah, my thing's bugging out again. So I take the derivative. Okay, I keep taking the derivative. So here I treat my x and y as constants. So this is a number in this case. So if this is a number, well then it becomes a 0, right? It's just a number. So I'm left with ln z. What's this? I add a plus. Then I have e to the xy and then this. Well, here I think of z as a variable. So when I take the derivative of this, I get 1 over z. So I get 1 over z. And so I actually just get e to the xy over z. Okay, looks like since this is 0, then I just take this out completely. because 0 times ln z is anything multiplied by 0 is 0. So I actually just have this as my final answer. Okay, that's good. Now let's do some related problems in the homework regarding that. Yeah, let's do some stuff there. Okay. So here we're being asked, so this is number 9. I kind of skipped a bit. Here we find the first partial derivatives. Of some function. So we do f of x, y, z. This is equal to 7x sine y minus z. Right? So I have an x, a y, and a z. Let's find each of them. Let's first find the f sub x. So how do I do this? Well, I just take the derivative. Here I treat my y and z as numbers. Like this. Take their derivative. I do a chain rule here. Yeah, I do a chain rule. Or honestly, I don't need to. Yeah, because I could just treat this and this as one number. 7 sine y minus z. Then my x, when I take the derivative, is just 1. So I'm actually just left with 7 sine y minus z. Just left with that. If I'm not wrong with my computation. Right? Because I treat my 7 and sine y minus z as numbers. Yeah. Okay, and let's do the same thing. F sub y. So now I'm treating my x and my z as numbers. How does this go? Well, here now I try to think carefully. I have my y. This is a number. 7x is a number. Z is a number. But then I just leave this 7x alone. I can leave it alone. And then I take the derivative of this. So I get, actually this is fine. I don't need to put parentheses. I take the derivative of this expression here. Hold on. This, I get cosine of the same thing, whatever's inside. And then I do a chain rule. So I take the derivative of this thing. Now my z is a number. And so that means this is 0. My y is 1. So 1 minus 0, that's 1. And so I'm actually just left with this. So that's it. Right? So this is 7x cosine y minus z. And lastly, for my z, well, I just do the same thing. So really the purpose of this homework is to just get used to the to taking partial derivatives and not getting confused by which ones are constants, which ones are not constants or variables. Yeah. So here my z is the one I'm trying to differentiate. My x and y are numbers. So I leave my 7x because that's a number. I take the derivative of this, so that's cosine of whoever's inside, in this case y minus z. And then I take the chain rule of that, Well, here I treat my z as the variable, so this becomes 1. Y is a number I treated as 0, so I'm left with -1. And so I just multiply negative. So this is the answer. That's it. So it's really just a copy and paste of the previous answer, but we add a negative, and then we're done. Okay. Next, let's do, yeah, we can do number 10, doesn't matter. So here again, we're being asked to find first partial derivatives of a particular function. So we're trying to find these guys. Right? And here's our function. We have w, which is equal to 6z e x, y, z. So this is a function of 3 variables, x, y, z, and its output is w. Right? And so the first thing we want to find here is my partial with respect to x. So that means I take y and z as numbers. So I take the derivative of this expression here. And what do I see? 6z is a number, so I leave it be. E to this, take the derivative of that. Well, we get the same thing. And then I do my chain rule on this x, y, z. Right? Here I see that, oh, y and z are numbers, so I leave it be. Right? So that's going to be, here I treat x as a variable, so I'm left with 1. So I'm left with y, z. So actually, that's fine. So our answer is just this, 6y z squared, because I multiplied both z's, e to the x, y, z, and that's it. Right? So 6yz, e to the x, y, z, I put a squared on my z, and I'm done. Okay, that's all the others. How about we take a look at the partial with respect to y? Well, if you want to do with respect to y, well, again, we do the same thing. And then from here, we take x and z as numbers. So we take x and z as numbers. So we leave 6z, right? We take the derivative of e to the, that doesn't look like an e. We take the derivative of e x, y, z, e to the x, y, z, and then we do a chain rule here, right? And then from there, we see that x and z are numbers, so we leave them be. I take the derivative of my y, will I get 1. So I'm left with, again, 6x z squared e to the x, y, z. I swear, there is a pattern here. Y and then it changes to x. There's something about that. I've been seeing it for a while now. Okay. And lastly, we take it with respect to z. So again, we take the derivative of my of my function. And then here we see that x and y are numbers, right? So here we leave the numbers behind. Here z is not a number. I would argue doing a product rule here, right? I could do a product rule. Do you guys think of a quicker way? Can't seem to find one. I would just do a product rule in this case. Yeah, I just do a product rule. I do something like, okay, maybe I'll split it here. And so I'm gonna get one function to be 6z, and the other function is e to the xyz. I could split it anywhere, it's fine. I just decided to do it this way. And then I do the same thing, but then I take the derivative of my other function, because that's the product rule, right? And then from there, now we take the derivative of each of these. So what is this derivative? Z is a variable, so this is just 6. So if we multiply, we have 6e x, y, z. Then we add. Here we have 6z and something. Here we have, well, if we take the derivative of that, we actually have e x, y, z, right? Times its chain rule. And here we treat x and y as numbers. So we'll have x and y. So here we'll have x and y. We'll have e x to the xyz. And here my z is just 1 because I take the derivative of that, right? And so what happens here, 6z, maybe I could put in my xy. There we go. And we're done. What else can we do? We can simplify maybe. I could factor out some stuff. I could factor out a 6 and an e. So let me factor these two terms out. So I'm left with 1 plus, I think this was xy, z. Yeah, because here I left these out. I left this and this out. Yeah, so I'm left with 1 and xyz. Okay, I wrote that like in a very bad way. Oh my goodness, xyz. Yeah, I'm writing it as a plus. I don't know why. And there we have it. Done. Now let me just input my answers. Okay. So here instead of y, I just change it to an x. But here is a bit interesting. Because here it's different. Okay. Let me submit, see what happens. Nice, got it. Okay. 11. Uh, okay. Here we are being asked to find the indicated partial derivative. You know, I've been wondering if there is such a thing called partial derivative, could there be a thing called partial integration? Probably. Okay, here we have a function of two variables. So we have an arcsine of xy. Oh, and then we're also given another info. We're saying that f sub y gives us a point, right? And it's asking me to find that partial derivative. I could find f sub y. It wants me to find this. So that's what I need to do. I need to find f sub y in terms of xy. And so I just take the derivative like normal. And here I treat my x as a number, but I treat my y as a variable. Here I immediately think of doing a chain rule. No, I mean a product rule, because I have two things here. So I would go like this. I add. Okay, no space. Let me move it. I like to move it, move it. Let me move it here. Okay. So, well, this is just a 1, right? This is 1. This one is, however, a bit different. How do I take the derivative of that? So, pala ko may cheat sheet. This is, there's a formula for taking the derivative of that specifically, of inverses. Yeah, there it is. So it says here that, I'm just going to recall, a regular derivative of, let's say, an arcsine is basically 1 over square root 1 minus x squared. And so from here, well, we just say that this is 1 over square root of 1 minus xy squared. And then here we take a chain rule of xy. And what's the chain rule of this? Well, here I treat x as a number, and so I leave that be. I treat my y as a variable. So if I take the derivative of y, well, I should get 1. And so I'm actually just left with x here. This is x over this. I could even do x squared y squared. I could do it like that. But I don't want to. That's fine. Okay. It's just a formula. Okay, I'm also taking notes because I don't know, this might be in a test. I feel like it will be in a test. Cool. Okay. So now that we have that, we just put them all together. And since I'm solving, I might try to simplify. Now this is y is multiplied here. So I get xy. There, that's my final formula. Now, is there a way I could simplify? I can't think of any right now. I'd leave it as is, I think. Yeah, I would leave it as is. So that was my first idea, which was compute for the derivative of f sub y. And then now, I try to find f sub y at a particular point. And so it's given 3, 1 over 6. So let me just quickly do that. So here's just plugging in to the formula. So sine, arcsine, I mean, we have 3 times 1 over 6. And so that's 1/2. This is 3 over 6. 1 minus 3 times 1 over 6 squared. And let me simplify. So I have arcsine of 1/2 here. 1/2, 1/2. What's that number? It's 30 degrees. Can I get this in radians? Okay, it's some number. So this is 30 degrees. Let me quickly convert it to radians. 180 over pi. That's my conversion. I cancel. I divide both by 30. This is 1, this is 6. I get pi over 6. Yeah. So this thing is basically pi over 6. So I get pi over 6. What else do I do? This one becomes 1/2. So I could say this just becomes like what? 1 over 2 of 1 minus 1/2 squared. And so this is 1/4. So this is 1/4. This is 4 over 4. 4 over 4 minus 1/4. This is 3 over 4. 3 over 4. This is 2. 2 times square root of 3 over square root of 4. Square root of 4 is 2. And so I'm left with 1 over square root of 3. So this whole thing is 1 over square root of 3. And then, is that good? I would say this is already good. But no, that's totally fine. I could rationalize this. Let me quickly do that. So I get square root of 3 over 3. So I get this basically. And then I can find the common denominator, which is 6. This is just 6 to square root of 3. Okay, I think this is the best way I could simplify right now. I can't think of any more. That should be it. So it's that number. Is it rounded? It's not rounded. So I have to keep it exact. Okay. This is 2 over 6. This is 2 square root third. I add a pi. Pi is a Greek letter word. Okay, let's hope I get it. Nice, got it. And okay, like 3 more items. I'm gonna go back to the textbook to talk about higher derivatives. Okay. Then after higher derivatives, do I talk about partial differential equations? I don't think we need to. Yeah, I don't need to talk about partial differentials. I just need to talk about derivatives. Okay. Let me do a brief intro on higher derivatives. Okay, let's do it here. So oh, so higher derivatives. So when we were computing derivatives before, well, we started off with just a first order derivative, right? So all you were doing was computing the first order. So if we were to do it in calculus 1, this is our function. Y is the output, x is the input, f is a function. If we take its derivative, well, we would just do this. And if we were to take its derivative again, well, we would have this. And if we were to take its derivative, okay, again, then we would have Okay, that looks funny. Triple derivative, like that. And so on and so forth. So what we kept on doing was a first order derivative. But what if we want a second order, a third, a fourth, a fifth, an nth order? So here, let's say we have a function of two variables. Then its partial derivatives would be f sub x and f sub y, right? And so we can also actually consider their partial derivatives. So partial derivatives of partial derivatives, right? And so we get the partial derivative of, okay, let me just write that down. So let's say if uh, f is a function, and let's say two variables. So namely, I mean f of x, y, right? Then we say f sub x and f sub y are also functions of two variables, right? But we just make the other one constant. um, so we can also get their partial derivatives. So every time we find a function of two variables, or three or four, or many, well, we can get their partial derivatives. So we can get the, let's say, the partial derivative f sub x, and then another one x, right? Yeah, so here we start from this right here, and then we get that partial derivative with respect to x. So that's how you're doing it. Another way is that we could get the partial derivative of x with respect to, oh no, my bad, it's in reverse. With respect to x and then with respect to y. So the first one was with respect to x and then respect to x again. The other one is with respect to x, then with respect to y. And then we could do with something with respect to y, then with respect to y again. And then something with respect to y, then respect to x. So it's those four things. Yeah. And these are called second partial derivatives, right? Because we're taking derivative again. Okay. We have some notations here. Yeah, let me quickly write them out. Or no, I'm not going to write them. I'm just going to display them using a screenshot. So here's what they look like, and don't be too overwhelmed because these are basic stuff. Well, I mean, not really basic if we haven't taken Calculus 1, but if we have taken Calculus 1, this is just adding more variety to it. But the notation is pretty much the same. Like you can see this one, we've seen that. This one, we've seen this. Doesn't really matter. But here we're focusing on these. And here are just different ways of how to write them. 1 and 1, 1 and 2, to indicate which variable. Then we also have this notation. That one's interesting. Yeah, so here with respect to x first, and then with respect to y, right? Here with respect to y first, then with respect to x. Those are, I guess, the only new ones. Because these ones, we have seen these before. It's kind of similar to this one, when we have a function of a single variable. But here we have multivariable functions, so it looks something like that. So let's say, or let's do an example. If we say, for instance, I'll write it in English. F sub xy, it also has this notation. So squared of that same function over, here we take the partial with respect to y first, and then with respect to x. So what's the meaning? Means we differentiate with respect to y first, then with respect to x. So I'm going to show ways on how to do. I'm going to show an example of that. But it's really just the same process that we've been doing before, but we're just doing it twice. That's all it is. It's really that simple. Okay, let me do, I'll do two examples here actually. I'll do two examples. So here we're being asked to find the second partial derivatives uh, of this one. So we have f. So here we're given a function of two variables. And this is equal to x cubed plus x squared y cubed plus, or no, not plus, my bad, minus 2x, no, not 2x, 2, 2y squared. Okay. Well, here we're first going to find their first derivatives, right? And then we find their other derivatives. Okay, let me do the first one. So let's try f sub x and f sub y. So what's f sub x? We take the derivative, we make y a number. We make x a variable. So let's do it. We have 3x squared. We have y is a number, so we can just leave that be. 2 in this case, x squared is just 2x. Y cubed. Negative 2 is a number. Y squared is a number. Oh, it's a number. And so this is just 0. Done. Right? Okay, now let's look at f sub y. Well, this is just, here we treat x as a number, and we treat y as a variable. So this one's 0. X squared is a number, so that's that. Y cubed, this is 3y squared, so I can just write 3 x squared y squared, and then minus 2y squared. I leave my minus 2 here. I bring down my 2 from my y squared, so I have minus 4y. And then that's it. Right? Done. Now we find our two variations of f sub x. We have f sub x x, and we also have f sub y x. So what does that mean? Well, that means if we find f sub x, let's just taking another partial derivative with respect to x of what we already have, right? And so again, we look at this and we see, okay, let's take the derivative. Here we make y a number. We make x a variable. So here we get 6x plus, this is 2y cubed. Here x is gone, so I just do 2y cubed. And we're done. And then I find my fyx. So instead of doing it with respect to x again, here we do it with respect to y. So I have that. Let me look at this thing again. So here I treat my x as a number. So this one's 0. 3x squared is nothing. 2xy cubed, 2x is a number. So 2x, I just leave it be. 3y squared. This becomes 3y squared. So this becomes 6xy squared. Right? And we're done. And let's also find the other ones. So let's find the ones for y this time. So we can find for y, now we're differentiating again with respect to x and with respect to y. So let's quickly find those two. So here we're doing it with respect to x of this thing. Yeah, so there's 4 variations to this when we have 2 variables. So here I treat my x as a variable and my y as a number. So let's see. This is just 0. Minus 4y is just 0. This one I treat 3 and y squared as a number. And so I have my x squared. This becomes 2x. So this becomes 6 x squared y squared. Right? Oh, I just realized I took out my 2. So this is 1. So this is just simply 6x. Okay, cool. And then lastly, let's do y. And here I get what? Well, I get something. What do I get here? I treat my x as a number, and I treat my y as a variable. So here I leave the 3x squared. I have my y squared. This becomes 6. 6x squared y minus 4. And that should be it. Yeah. And so it turns out this is not a coincidence. Oh, what did we see? xy and yx are the same. Look at that. What does that mean? Here we notice that f sub xy is actually equal to f sub yx. And it turns out that the mixed partial derivatives are equal for most functions that one meets in practice. Oh, so that's the theorem. So there's actually a theorem that someone proved. So this was proven by a French mathematician, Alexis Clairaut. Not gonna. Yeah, never mind. Okay, I mean, he's a he's a child prodigy in math. He's read L'Hopital's textbook on calculus when he was 10 years old. He presented a paper on geometry to the French Academy of Sciences when he was 13. At 18 years old, he published he published, okay, it's a French word. Okay, it looks like a French word, yeah. But he published some paper, I think, but I think it's research. He published like a research paper on 3D analytical geometry and calculus of space curves. So he did something with calculus, basically. And this was his theorem. Okay, let me just clear. I give up. He's a French guy, so I don't know. So here we suppose, so these are the assumptions. Oh, F is defined on a disk D. I'm assuming a disk is a quadric surface. And this function contains a point. And we'll just call it AB. And we're saying here that if functions f x, y, and yx, and we're saying that they are continuous on D, the quadric surface D, or the disk D, then here's the theorem. F sub xy at that point is the same as f sub yx at the same point. So that's the theorem of Clairaut. And apparently we can also define a partial derivative of order 3. So we can do that. So a third derivative. And then we can apply Clairaut's theorem. Okay, let me just quickly show. I'll show you what that is. So I'm going to say partial derivatives of 3 of, let me be specific, order 3 or beyond or higher can be defined. So let me just try some stuff out. So here, I'm going to say this is an order 3. So we take a partial derivative with respect to y, and then respect to y, and then respect to x. Let me do this. Okay, there must be a reason why it's making us do that. We take a partial with respect to y. Oh, and then the second derivative with respect to y, and then respect to x. Where is this coming from? This comes from this. And then this comes from this. Right? Okay, so it's writing it in that notation. Oh, and then from there, here's the new notation. Now we make it 3. And then we do y squared x, or with respect to x. There we go. And so that's the notation for partial derivatives. Can I make it general? I guess I can. But then I have to know what these numbers are. Never mind. I'm not going to make it general. But I know the... Okay. And let's say we use Claire... Oh, no. What's the person's name? Clairaut's theorem we say that this third order derivative could be switched around. If, well, we can see that these functions are continuous. Right? Or at least that's one of the definitions that I know. Because I know, or at least my professor told me, in higher level math, there are particular functions that are not continuous. But if we know, let's say we have a polynomial function, then that's guaranteed to be a continuous function. But there are some functions that are not continuous. I mean, for instance, we have piecewise functions. Piecewise functions are not continuous, especially if their conditions are not, well, exact, or they're not, basically they have holes and gaps. Yeah, we have piecewise functions, and then among others, there are other things that I don't know. But there might be, I'm not going to say it's only continuous, because this might be an undergrad. No, this is an undergrad textbook. But I wouldn't simply assume to apply this person's theorem just because functions are continuous. But that's tentative for now. That's tentative. Okay, let me go through a final example in the book, and then I'm going to do some examples from my homework, and then we'll see how it goes. So here we're being asked to calculate f sub xyz. Oh, oh, we're being asked, what? Huh. Is this a fourth order? X, X, Y, Z. If, let's say, our function of three variables is equal to 3x plus yz. That's interesting. Yeah, here I just, what the hell? There are four things now. Okay. Yeah, I'm not blind. There's definitely four things here. Um, that's fun. Okay, I guess we can start. So first let's find f sub x. And so we take the derivative of this function, we get a cosine of whatever's inside. Then we take the chain rule of this thing. Here we say y and z are numbers, so that's 0. We're left with 3. So our number is just, or our answer is just this. And then we do f sub xx. So now we differentiate it again in terms of x. So we're looking at this function. So here I'm leaving the 3. I'm taking the derivative of this, so I get negative 3 sine of whatever's inside. I leave these y and z as a number. I take the derivative of 3x, I get 3, so it's actually just negative 9 sine. And I do it again. Here I have x, x, y. Yeah, so actually the order doesn't matter using Clairaut's theorem. He just happened to do it, or the textbook just happened to do it in this order. But I can do it in any order I want. Okay, so let me see. So now I take the derivative of this with respect to y. So I'm actually taking derivatives 4 times. 1, 2, 3, 4. because I'm doing it for another one here. But let me finish this one. I'm leaving the -9 alone. This one's a cosine of 3x plus yz. I'm differentiating it with respect to y, so I make my x and my z a number. So I'm actually left with a y here. And I'm left with a z. Yeah, I'm left with a z. Because this one's a 0, 3x is going to be a 0. And so this is just -9z cosine of whatever was inside. And lastly, let's differentiate it in terms of z. I leave my -9 alone. My z is a variable. Uh, here's the final answer. I don't want to go through the computation anymore because I know that it's going to be quite long. I'll just go through it in the homework. Okay, and we're done. It's a fourth order. Okay, now let's go to my homework. Let's do some stuff there. Okay, we have like how many more? How many more stuff do we need to answer? Because I went through it in like random. Oh, so 14, 15, and 16. Okay. They're all okay. So let's do 14. Here we're being asked to find all second partial derivatives. Right? And so I have f of x, y. This is equal to sine 2, sine squared. Then I have mx plus ny. And I'm assuming m and n are just some constant values. Yeah, I'm just saying that just to be super clear that these are just numbers. Okay, let's do fxx. Oh, we're actually going to do all of them. Fxx, xy. Okay, so it's so the first thing we want to find is f sub x and f sub y, right? So my f sub x, so I take the derivative of this thing. Here I can write it like this. Square. Then I bring my square down here. So I get 2 of whatever was inside. I take the derivative of this thing. And so that's cosine of this. And then I take the derivative of this thing. So here, notice how I'm kind of like peeling off everything. And then here I see, well, I treat my y as a number and my x as a variable. So I take the derivative of mx. Wait, let me just copy. So mx is just m. And then ny, well, that's nothing because y is 0. So I just have m. So in this case, we'll just write it in this way because it looks nice. And we're done. Let's look at f sub y. So again, we take the derivative. I'll skip the steps. I'll go directly here. Okay. Now I look at x as a number and y as a variable. So I'm left with n actually. 2n. And then here it's just a number, so I'm left with 0. mx. And we're done. Okay. Next thing we want to do is find those 4 second derivatives. Let me find fxx, fxy, fyx. So if I find xy, I found yx. So I actually only need to technically find 3. This is continuous because it's an elementary function, which is a trigonometric function. So it would look something like, I don't know. If I remember my science, something like that. And it just goes on and on and on. No gaps, no holes, so it's continuous. So we can apply Clairaut's theorem, right? So let's find f xx. So we take the derivative of this thing here. 2m cosine mx plus ny. Well, I leave my 2m alone because I treat it as a number. My cosine, no, that's different. Now I make it in, I take the derivative of that, so I get the negative sign. Let me just, okay, I'm just completing the whole solution. But basically we take the derivative of this, and then we see that, oh, okay. Well, cosine is negative sign. And I wrote cosine, okay. So cosine becomes sine, and then I copy. And from here, I take chain rule. So I take the derivative of whatever was inside my trig function. Then from there, okay, I think I should have done it in I should have done it here. Yeah, somewhere there. There we go. Okay, this looks good. And then from here, well, I look at this thing. Well, I'm taking the partial derivative with respect to x. So that means my y is a number. And so I'm left with m here. This whole thing is m. So actually I just get negative 2m squared sine of mx plus ny, and we're done. That's one of them. Let's look at xy or yx. Any of them should work. Now let's choose which one. We can do y and then differentiate it with respect to x. Or we can do x and differentiate it with respect to y. I'm going to be honest, any of them should work. I'm going to go with differentiating it with respect to x. Okay. So I look at my y function here, or my f sub y, and then I take that derivative, and I say that here, no, this is my y, and I'm doing it with respect to x. So my y here is going to be a number. And then my x here is going to be a variable. Okay, let's quickly do that. So I leave 2n alone. I take the derivative of my cosine function. Well, this is negative sign. So negative 2n sine of whatever was inside, right? And this should give me oh, I forgot chain rule. So what is this? Again, this is my f sub y. Now I'm doing it in terms of with respect to x. So I make x my variable. I make y a number. So I'm left with negative 2mn sine of whatever was inside. If I did it the other way around, would it have worked? Let me see. So that's also how I check. What if I do this one and I differentiate it, or I take the partial with respect to y? So I leave 2m, this becomes negative 2m sine of this. Take the chain rule. Uh, this one. So I got negative 2mn sine of, yeah, so I get the same thing actually. I get the same thing. And lastly, let's do f sub y. So I look at this thing, and then I differentiate it with respect to y. So I leave my 2n alone, because that's a number. I take the derivative of my cosine function, and I'm left with, well, this becomes negative 2n sine. I take the chain rule, and what am I left with? My y is a variable, my x is a number. So I'm left with negative 2n squared sine of this. And we're done. I have my three things. One of them is equal to the other. So I have negative 2m squared sine of mx plus ny. Then I have my other one. For my yy, I just change it. I change my m to an n. That's it. My m to an n. Then for my other two, well, it's just this thing. Two mn. I do the same. I just copy and paste these stuff. And I should get it. Oh, I got them all. Okay. Why is that? Um, okay, I didn't get any of them. That's funny. Yeah, that is weird. Okay. Either I got them wrong or my homework's not registering them properly. It's one of those. But we'll see. I don't know. Oh, it's sine squared. So that's why I was wrong the whole time. I totally forgot about the, or no. Yeah, because if it was sine squared, no way I did my differentiating wrong. This is just sine of whatever's inside squared. If I take the derivative of that, I would get 2, right? And I would take the derivative, I get a oh. So I do this and then get the chain rule of this whole thing, which would give me chain rule of this. Oh. And then that would be cosine and then chain rule of that. And then, okay, okay. I see what I did wrong. Yeah, I messed up the whole thing. Yeah, I messed up yeah, that part. Yeah. Um, okay. Am I gonna go through the computation again? Because that was tedious. 2 of mx, right? 2m squared cosine 2mx plus n y. Nice switch here. Yeah, now I have everything in cosine. And then I just do this. 2m squared cosine. Did I get that? 2mx and y. 2m squared times cosine. And inside that cosine, it's 2 times mx plus ny. Then n squared. And then my x, y, and yx should be the same based on that theorem. And that should be it. Question mark. I hope it is. Yeah. I messed up the chain rule of all of it. Yeah, this was my bad. Um, yeah, if I messed up one of them, I messed up all of them. So I messed this one up completely. This part. Yeah. Okay, let me actually do it. F sub x, right? So we assume that this is squared, so we put 2 of this thing, right? Then we take the chain rule, so we get cosine, and then we get chain rule again. And so what is this? I treat my x as a variable, so this becomes m. So 2m. Done. Then my f sub y, well, I do the same thing. So 2 sine. I'm leaving space because I know I'm going to have a number. Take a chain rule. Take a chain rule. And then, yeah, it's all chain rule, chain rule, chain rule. Because these are what we call composite functions. Now I treat my y as a variable, so I get n instead. And we're done. Now here we find, I'm going to do this a bit quickly. Xy, which is just the same as the other one. But the idea was there. Like the process of taking the derivative is mostly the same. I just messed up not getting the chain rule in the first place. That's how it affected all of my computations. Because you see in math, if you get one thing wrong, you get all of them wrong. Okay, so let's see. We have like 4 things here. I'll leave my 2m because that's nothing. Uh, I'll take the derivative of this thing. So that's going to be, and my process should be the same, so I shouldn't have to worry. I take the derivative of this, and then I leave my cosine. Then I do another one of these. And I take the derivative of my cosine. Okay. Where was it? Oh, I lost it. There we go. And then from there, okay, let's take the derivative of this. So this is cosine. This is mx plus ny. Chain rule, so I do m here. M cosine. What's this? This is sine. I do a chain rule. So I do m. So I get m squared, or not yet. I get m cosine squared of that thing plus m sine squared of that thing. Don't tell me I just get an m. That's too funny. Let me see. I must have. There's no way I messed it up again. Because I have a 2m here. Oh my goodness, did I mess it up again? 2m sine of this, cosine of this. Then I did a chain rule, so I computed. I get cosine, I get m cosine, and then this. So I just combine them, I get this. And then sine, and then here I get, oh, I get minus sine here. My bad. So I get minus. So this is, yeah, this is minus m. And then I could factor it out. I get cosine squared minus sine squared. And I think it might be a trig identity. And it's not. Obviously, it's not. Let me see. How did he do it? M sine, or did I do it wrong in the first place? What? That's so, wait a minute. How come I got two? What is that? Oh, is sine times cosine a trig identity? Oh my goodness, is that a trig identity? Oh, it is a trig identity. Yeah, sine and sine multiplied by cosine is a trig identity. Yeah. So, let me highlight. Just like a note. If we were given a sine x, cosine x, that's basically 1/2 of cosine 2x. So that's where they got that from. Yeah. And so that's why I have to do for both of these. And then get these. Yeah. Okay, that wasn't expected. But that's what I should have done. And so I just have yeah, I have m sine. Okay, why is it sine? if it was a okay, what? Now what's the issue? Let me okay, substitute to that thing. Is that another tree identity that I don't know? No, no way. Ah, mostly trig stuff that I don't. Yeah, it's the trig stuff that's getting my answer off. But basically, if we get what is this? Um, I think it was 2 sine x, cosine x. So it's sine 2x. I think I could have done it. Uh, yeah, so the idea was, well, to get my sine squared, right? So it's not even this. My sine squared, let's just call it u, where u is mx plus ny. And this can be, or when I take its derivative, I get 2 sine cosine, right? And I take its derivative again. No, I don't take the derivative. This is the same as sine 2u. And so from there I have 2, or well, I have sine of 2 of mx plus ny, right? And then I multiply it by m because of that chain rule. Then here it's the same thing, but I multiply by n. N as in nice. Yeah, and then that's where the other computation comes in. Yeah, just a little miscalculation on my part. It's because of these weird stuff. But if we do calculate them, the process is the same. Then here are the final answers gonna be. I'm just gonna take a, there we go. Those are the final answers. Okay, I'm just gonna skip that for now. Too much trig stuff is going to explode my brain. Okay, we have 2 more questions, and then we're done. Number 15. We have a temperature at some point, right? So we have a temperature at a particular point. We'll call this point xy, and it's on a flat metal plate. So it's basically on a surface, and it's given by a function of 2 variables. So t, x, y, and this is equal to 45 over 3 plus x squared y squared. T is measured in Celsius and xy in meters, where T in Celsius and the xy in meters. Okay. And we're being asked to find the rate of change with respect to the distance at the point. And so here we're just basically finding the partial derivatives of two things, right? So we're being asked, our task is to find rate of change of temperature. And this is in Celsius per meter at this point with respect to distance to 1 in the x direction and y direction. So here, this is kind of obvious as to what it's asking. It's asking us to compute partial derivatives. So in the x direction, well, you want to compute with respect to x. And then in the y direction, we want to compute with respect to y. And then we plug in what we need. So first we find t sub x and t sub y. So here we're finding the two rate of changes in those points. Okay, so t sub x is the derivative of this thing. Oh goodness me. Okay, let's just do it. So quotient rule, I'll take the derivative of this whole thing. Low derivative of high minus high, derivative of low over this squared. And so what is this? Well, this is 0, so this is gone. Negative 45 times, what is this? We're doing it with respect to x, so this is the x direction. Well, this is supposed to be, y is a number. So y is 0, this is 2x. So I have 3 plus 2x. And so that's my answer. Negative 45, 3 plus 2x all over my denominator, right? And now let's find it at particular points. Right? So let's do it. Tx specifically at that point. Well, here we just plug in. Right? What is this? Let me try to 4 plus 7 plus 3, that's 7. This is 315. This is what? 3 plus 4, 7 plus 1, 8. 8 squared, that's 64. 315 divided by 64 is that a thing? Do I round it? Okay, but it's basically this. So temperature is decreasing. Okay. Then let's look at t sub y. So again, I go here directly. Okay. And what is this? This is just a 0. This one, here we treat x as a number. And so we have 3 plus 2y. Yeah. So we basically have this, but instead of x, it's y. So I'm just taking shortcuts. I'm trying to be quick. And then to compute at that point, we just plug in what we know. This is 1, right? Yeah. And this is, oh, okay. Here I get 64. This is 64. This is 3 plus 2, 5. This is 2, 2, 5. I hope that's right. If not, that's okay. You plug in the points. What? Did I mess up? Oh, this is supposed to be, oh my goodness. This is supposed to be a 0. So this is 2x. And so that means this is 2y. My bad. And so that means this is 2 times 2. So that's 4. And so this is 180. And then I can simplify, right? Okay, these are just some careless mistakes. So it's 4. Oh, 45 over 16 in the x direction. In the y direction, well, it's what is this? Oh, let's do y. This is 2 times 1. This is 90 over 64. Okay, that's the same. Could I simplify? Yes, I could. I could divide both by 2, I'm assuming. I get 45 over 32. Okay, there you go. And then that's it. Celsius per meter. Sure. I'm gonna enter a fraction here. So the first one was negative 45 over 16. And then the second one was negative 45 over 32. And then we're done with that. Yep. Okay. Okay, last number. So here we have a total resistance R, and it's produced by 3 conductors. And these three conductors have resistances. With R1, R2, and R3. And they are connected in a parallel. Okay, this is some science class. Connected in a parallel circuit. And so that's a formula. 1R, 1 over R is 1 over R sub 1, 1 over R sub 2, 1 over R sub 3. And here we're being asked to find a partial of R with respect to R1, right? So this is, well, this is a function that contains R1, R2, and R3. That's a function. And this is basically saying we find a function of R sub 1. So this is a three variable thing, right? So let's do it. Uh, I mean, we just, oh, but then the thing is, we don't have it in explicit form, do we? Or no, I'm kidding. I think we do. I'm pretty sure we do have it in explicit form. Yeah. Oh, we just have to make them. Okay. Let me Let me review for a bit. What in the world did I do? We treat Okay, given three variables, we treat two of them as constants. We have a certain output. Oh, we basically treat them as constants. Oh, that's it. We treat them as constants. Well, now, okay, let's say we do that. Uh, so we do with respect to R1. We treat R2 and R3 as constants. So we're gonna have um the other problem is this is not explicit, right? Or actually it might be. I'm not super sure. How do you solve that part? So we take its inverse, huh? Okay, let me. So, okay, the first thing we want to do is you want to express R explicitly, right? And so this is the same as saying R negative to the power of -1, right? And then now we can take the exponent to get to the other side to get this, right? What do I mean? Well, let's say this was the answer, right? Let's do a value. Um, I don't know. Let's say y equals. Actually, no, I can't. I multiply everything by a power of -1, basically. So this will become +1. That's what I'm trying to say, right? Uh, and then from there, I get 1 over this thing. And now I've solved explicitly for R. Right? So after, well, doing that, hmm, I'm trying to double check. I'm actually a bit confused because of the letters as well. Okay. Uh, yeah, I'm still trying to figure it out. Um, okay, wait. Me. Okay, let me just reiterate what the video is saying. What the video was saying, this is a bit weird for me. Uh, this is technically the same as R inverse. So that's what he's saying. And so from there, he can say that the partial of that inverse with respect to R and if we multiply that with the partial of R with respect to R1, then we would get the partial of this thing. Oh, it's because you cancel this thing. And so you get partial of R to the negative 1 with respect to R, which is the partial of this with respect to R1. So that makes sense. And then from there, this is negative R to the negative. So we're just taking derivative of this thing. Hmm. So if we take the derivative of this thing now, we have constants. These are zeros. This one is R1 to the negative 1. And so we take the derivative of that, we get negative R1 to the negative 2. Now we have this thing. So we just isolate it. So here we just do some isolating. Here we can take out negatives. And this is, we can switch their places. And we're done. R squared over R1 squared. Yeah, so I think that was the trickiest problem out of all of the ones here. Definitely super tricky. It's hard to come up with relationships like that. But we'll see if we got that one. So we do R squared over R sub 1 squared. And we got it. Okay. Um, that's all for this video. I hope you guys learned something. I hope you enjoyed. More importantly, enjoyed. And yeah, I'll see you guys in the next one.